Hi. Um, Let us recap some of the principles of electrostatic potential and capacitor, how the capacitance work, how we can calculate, and then I will cover some of the topics that you mentioned in your chat about the dipole, capacitance of a dipole, and so forth. So let's start with capacitance. So very simple, just kind of like a refresh. So when a charge Q is applied to the conductor, any conductor which can carry the electrons or carry the current, when any charge when any charge Q is applied, then the voltage will rise, and voltage will be kind of like proportionate to Q. So basically so Q will be proportionate to V. As voltage increases, um, the charge will be increased and vice versa, right? So in general term, we can write Q is equal to CV, um, where C is the capacitance, V is the voltage, and charge is Q. So capacitance C is Q over V. So in general, as charge is uh, applied, voltage will go on. So capacitance, the unit of capacitance is farad. So anything that we mention, it will be in farad, and 1 farad is 1 coulomb, 1 coulomb over 1 volt, right? So first equation to consider, C is equal to Q over V, or V is equal to CQ. First thing, kind of like to just connect. So we'll just keep the equations in order, right? Then comes capacity of an isolated spherical conductor. So let's say there is a spherical conductor like this, and we applied charge Q right in the center. This is the outer surface, so everything is charged, right? This is the center, and this is the radius of the sphere. So in these particular formula, uh, positive charge will be concentrated in the center. So the formula for the voltage V is equal to Q over 4 pi epsilon 0 R. Now epsilon 0 is the permittivity of a free space, or a free space, and the value of epsilon 0 is 8.854 times 10 raised to minus 12, something again, um, to note. Now V is equal to Q over C, right? So in this case, C then become 4 pi epsilon 0 R. So another equation to kind of like keep in mind, that for a spherical isolated conductor, the capacitance is calculated 4 pi epsilon 0 R, where R is the radius, uh, and epsilon 0 is permittivity, or a constant, whatever you want to call, 8.854 times 12 raised to minus 12 farad per meter. That is the unit. So again, recap: Q is equal to CV, so C is equal to Q over V. This is the capacitance, the unit of capacitance measured in Faraday. Q is the coulomb, the charge, V is volt, and then if we are trying to calculate the capacity of an isolated spherical conductor, then this equation will come into play. The voltage will be Q, or the charge which is applied in the center, radius of the sphere, and Q over C. C in this case, so basically capacitance is kind of like denominated as 4 pi epsilon 0 R, right? So this is first concept. Second concept is in general regarding the capacitance. So the capacitor, symbol of capacitor is this. It stores the energy whenever charge is kind of like applied to two plates. So if you are considering two plates like this, then these are the two plates, and the charges are applied. So basically this become a capacitor. Capacitor in series is like this. So this is the series function. Capacitors in parallel, these are the parallel capacitors connected in parallel, right? So if there is any example of kind of like very simple example of calculating the total capacitance of series capacitor or a parallel capacitor, and then you have to find the total capacitance. Then if they are connected in series, then it is 1 over C, which is equivalent capacitor 1 over C1 plus 1 over C2 plus 1 over C3. This is for series. And if it is connected in parallel like this, then it is C is equal to C1 plus C2 plus C3 all the way up to Cn. So another formula to consider, that when capacitors are connected in parallel, 1 over C, which is kind of like the resultant capacitance, total capacitance is 1 over C1 plus 1 over C2, 1 over C3. And if they are connected in parallel, then C is Cs, or resultant capacitance is C1 plus C2 plus C3 plus Cn, right? That is another formula to remember. Then we will go with parallel plate capacitor. So this is sort of parallel plate capacitor, right? And let me erase it so I can so different type of capacitor, right? We said that these are kind of like a plate capacitor. Imagine that these are the two plates, and they are being applied voltage, so they are kind of like positive, 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 and negative, negative charge. So if air is sort of a dielectric, or air is the medium, then capacitor C, so the capacitance formula is epsilon 0 into A over D. Epsilon 0 is the permittivity of free space that I wrote earlier, 8.854 times 10 raised to negative 12. A is the area of each plate, and D is the distance by which these two plates are separated. And we are considering air as the medium. Let's say there is sort of a dielectric. If there is any dielectric medium, something you place in between the two capacitor plates, then there will be a dielectric constant of that material. In that case, resultant capacitance will be K epsilon 0 A divided by D. So this is another formula for sums that we need to keep in mind, right? Now let's say there is a thick plate. This equation is not considering anything with the thickness of the plate, but let's say there is a thickness. Then the capacitor for resultant capacitance formula will become C is equal to epsilon A divided by d minus T 1 minus 1 over K. So this is simple air as a medium. This is very thin dielectric. This is sort of a thick dielectric material in between the capacitance, and the distance is kind of like this. So the D is distance, T is the thickness of the dielectric material. If the thickness is given, epsilon 0 again, free air permittivity, area is the plate, K is the dielectric constant of that material, right? So these three are kind of like parallel plate capacitor formula. Just in case if any example or any sums that comes up in here, right? Now there are some examples that I saw, and we may end up in kind of like solving later on. But if there is sort of an energy calculation or energy thing comes into play, then what is the energy stored in between this parallel plate capacitor, right? So basically energy is nothing but the work that we need to do to bring kind of like a charge from one particular distance to that point Q, and it is given by 1/2 CV square. So basically if the energy or potential energy stored that we are trying to calculate, U is equal to 1/2 into CV square, right? So now C is nothing but QE. We can kind of put any alteration in here. If energy stored is asked, then we can put the capacitance and the voltage applied. We can derive it in capacitance again. We says Q is C is equal to Q over V, or Q is equal to CV, right? So anything is given, we can substitute. If there is an energy stored in a capacitor or a parallel plate capacitance that is being asked, then we can do this. If we need to solve the sum that 2 or 3 capacitors are coming together, and what will happen to the charge, right? There are some examples that I have read that if one capacitor is charged up to one particular point, another capacitor is charged to another particular voltage or so. If we are connecting, then how we can calculate the potential, right? What would be the resultant potential if these two are coming together? So it is nothing but V, that is the total voltage, right? When two connectors are two are coming together, so it is total charge divided by total capacitance. And excuse me for my handwriting, not so great, but this is V is equal to Q1 plus Q2 plus Q3 all the way, capacitance C1 plus C2 plus C3 all the way, and Q is nothing but CV, so it is C1 V1 C2 V2 divided by C1 plus C2, right? So if we are asked to calculate the voltage when two capacitors are connected, then this is the formula: C1 V1 C2 V2. If two are connected, then C1 divided by C2. So one more formula to remember, but this is for examples that has common potential or resultant potential. From that, there is another one, which is sharing the charges. When we said that there is no loss of absolute energy, right? Then basically what we said, U is equal to 1/2 CV square. So total resultant charge, if we need to calculate, then U1 minus U2. If we are calculating that, then it is C1 C2, and then into bracket V1 minus V2 square divided by twice C1 plus C2. If something of that sort, then what would be the sharing charges, and there is no loss, then the sharing charges or the energy, potential energy, is this, right? So resultant voltage V is C1 V1 C2 V2 divided by C1 plus C2. If two capacitors are given, capacitance is given, voltage is given, then final potential after they are connected together. And the energy calculation, U1 minus U2 C1 C2 V1 minus V2 square divided by 2 C1 plus C2, right? Some basic refresher before we solve the examples and go further. You mentioned about one more thing about the examples, and I know you must be aware about it, but the capacitance is given in different units. So if it is given in millifarad, it is 10 raised to minus 3. It is in microfarad, 10 raised to minus 6. If it is in picofarad, 10 raised to minus 9. So 10 raised to minus 12. So if something is given in terms of word that the capacitance is let's say 10 picofarad, so then it will be 10 multiplied by 10 raised to minus 12, so this is picofarad, this is microfarad, and this is millifarad. So -3, -6, -12. So these are all SI units. But in example, if something is kind of like given in word, then we should know that pico is -12 and micro is -6. Pretty simple, right? Capacitance of a spherical conductor. So typically, like, we are considering that this is the sphere, the charge is applied in the center, radius r, and this is the surface of this conductor, right? So these are outer surface. Let's say we need to calculate simple example. Capacitance of a spherical conductor of a radius r. C is, we said that earlier, C is 4 pi epsilon 0 r square. Let's say there is an example that we are bringing. So what would be the capacitance of the earth, right? So earth is a sphere and the radius is 6400 kilometer. If we are consider r, or plug in r as 6400 kilometers, then earth capacitance will come as 4 times, let's say pi is 3.14 times 8.854 times 10 is to minus 12 radius square, right? So r is equal to 6400 and we are converting it to meters square. You calculate this and you will get earth capacitance as 711 microfarad. So kind of like a common question. I have seen this question in couple of tutorials. So this is kind of like, this is how you are kind of like going to plug in the value. Epsilon 0 is again permittivity of a free air. Earth radius, typically they want you to know that earth radius, earth is a sphere and its radius is 6400 kilometers. So simple question, multiple choice, that what is the capacitance of earth? This is the answer, 711 microfarad, right? Now you mentioned about electric dipole and the capacitance. Formulas are kind of like key to remember, but I'll tell you the concept that what exactly the potential due to system of charges. So there are two things that needs to kind of like consider. So potential due to system of charges. Then let's say there are so many charges kind of like acting. We are kind of like keeping an eye on different charges. So let's say this is charge q1 and this is radius 1, right? So this is kind of like r1p. Let's say there is another charge q2, this is r2. Let's say this is charge q3, this is r3p. And let's say this is q4, let's say this is q5. So there are various charges acting here at a different radius, right? So basically the resultant voltage will be v1 plus v2 plus v3 everywhere for every vector in a sense. And sometimes it is kind of like coming into vector, or it has that hat sign on it. But right now let's just consider that this is individual charge. So v is v1 plus v2 plus v3 up to whatever n. So that is nothing but 1 over 4 pi epsilon 0. And now we have to find out the resultant radius and charge. So it is q1 over r1 plus q2 over r2 plus q3 over r3 and so on, right? Because the basic equation that we had. So let's say potential outside of the sphere, again this is applied in the center q, this is r, this is surface. So the resultant radius is kind of like outside. So let's say r is greater than the resultant, or outside of the radius, r is greater than or equal to r, then v is 1 over 4 pi epsilon 0 uh, into resultant q over r. So this is potential due to the system of charges. There are various system of charges. We are considering r or small r, the radius is greater than or equal to something which is outside. So this is our r is greater than this r. If it is outside, then this equation will come into play. V is equal to 1 over 4 pi epsilon 0 q over r, right? And if um, the electric field asked within the shell, electric field within the shell will be always 0. So now this will lead into your understanding about potential due to an electric dipole. So this was kind of like a fundamental equation. What is dipole and how this surface come into play? Let's say here is kind of like an origin, or here is the center. This is our center P, and there are two charges. One charge is Q here and another charge is negative Q on the bottom. They are at the equidistance. So let's say this is kind of like center. My center is here, P. This is my A, and this is my A, and we have to kind of like bring the charge from point P. So what will happen if P is somewhere here? Then this triangle will happen. This is my theta, right? Negative charge, positive charge. This is the point P. So I need to calculate a work done basically to bring a charge from P to P, and this distance is, this is A and this is A, this is 2A, correct? This is angle theta, and we are saying that this resultant radius is r. This is my r1 for q, this is my r2 for q minus. So this becomes sort of a dipole, or something that is kind of like at the angular distance. So we are kind of like calculating that how exactly the resultant voltage will be. So typically we know V is equal to 1 over 4 pi epsilon 0 into bracket. Now we have to calculate this charges, right? So it will be q over r1 plus or minus, we need to find out q over r2, and in this case it is minus. So instead of plus sign, this is minus because we are calculating minus q. So q minus q, p, r1 r2 r, and this is theta, something to kind of like remember, right? So r1 and r2 are kind of like a radii distance of the charge from point P. So let's say and now we need to kind of like calculate this too. Now this angle, maybe you were kind of like confused here while applying that trig thing, right? So r1 square will be r1, so we are kind of like, let's say calculate r1. So r1 square is nothing but r square plus a square, and this is, if we are taking cos, then it is 2ar cos theta, a square. Let me take this in here. So this angle minus, so this is just simple trigonometry problem. We are just calculating this. We are trying to solve for r1 square. So r1 square is equal to r square plus a square minus 2ar cos theta. And then similarly, if we are calculating r2 square, that is r square plus a square minus 2 ar cos theta, right? Because this angle is, as it shows, this is theta and the same thing is for theta. So there are two triangles. Basically it's like normal trig that we are solving. So if we are simplifying this and finding R1 square and plug it into our voltage equation, V is equal to Q over 4 pi epsilon 0 into 2a cos theta over 2a cos theta over R square. So resultant V will become V, I am writing over Q over 4 pi epsilon 0 into 2a cos theta divided by R square. This is nothing but P cos theta over 4 pi epsilon 0 R square. And in this case, basically P is equal to 2 into QA. So P is nothing but 2. So A is the distance of this positive charge, and that will become P. And P cos theta is equal to P dot R hat. So if we are kind of like putting in a vector, so vector will come up with the direction as well. So it will denote the direction, right? So it's a vector formula. So this is how the dipole equation works if the direction portion is given. If direction portion is not given, and if we are just calculating as a scalar entity, then we will become 1 over 4 pi r square into P cos theta. So that is the equation for dipole potential calculation you need to remember, right? That is how the logic and complex formulas and everything is solved, simple trigonometry, but this is sort of and these two are equidistant, so positive charge and negative charge are at equidistance, and we are trying to pull in or calculate the voltage differential to pull P towards here. So some sort of a work done in this direction, and that's where the vector comes into play, right? Now this, if this P is kind of like lies on the axial line, right? So in that case, so this is equatorial line and this is axial line. So that's where kind of like a special case comes in. If there is anything in the verbiage that point P is lies somewhere. Now if it is kind of like lying on the equatorial line, then basically voltage will be 0. Why? Because cos 0 is 0. So if you plug in 0, so automatically voltage will be 0. If it on the axial line, then it will be at the 90 degree or right angle. So cos 90 is 1. And in that case, we will become P over 4 pi epsilon 0 r square. This is 1, right? So if it is axial, then cos theta or cos 90 is 1, so it is P over 4 pi epsilon 0 r square. If it is equatorial, then it is like this, cos 0 is 0, so this resultant whole thing will be 0, so in turn voltage will be 0. Something to remember if it is kind of like a verbiage that they are going to use in electric dipole example, right? So I leave this video up to here. I will send it to you. You see if you are getting it. If this is useful, then I'll record some more. But I hope that the dipole concept is a little bit better after this. So I'll WhatsApp you. You see, and then if we need to do it together, then we will find some time to do it together. If not, you can get into this and then we'll try to solve some problem later on once we will refresh thought process, especially for me, and then we'll go and do some sums, right? Okay, bye.